Welcome to this coding problem walkthrough. Today, we'll explore LeetCode problem number 2028, find missing observations. In this problem, we aim to find an array of missing dice rolls that satisfy specific constraints. Let's dive into the details and solve this step by step. In this problem, we are tasked with finding the missing observations from a series of dice rolls. The input includes an array called rolls, which represents the results of m dice rolls. Each roll comes from a standard 6-sided dice, meaning valid outcomes are between 1 and 6. Additionally, we are given two integers, mean, which represents the target average of all the m plus n dice rolls, and n, the number of missing rolls we need to determine. Our goal is to calculate the values of these n missing rolls such that the average of all the rolls matches the given mean. If it's not possible to find such values, we should return an empty array. The solution must ensure that the missing rolls are valid dice rolls, meaning every value must be between 1 and 6. To understand this problem better, let's look at an example. Consider the input where rolls is 3, 2, 4, 3, the mean is 4, and n is 2. First, we calculate the sum of the given rolls, which is 3 plus 2 plus 4 plus 3 equals 12. Next, we determine the total number of rolls, which is m plus n equals 4 plus 2 equals 6. The target sum of all rolls can then be calculated as mean asterisk m plus n is equal to 4 times 6 equals 24. Subtracting the sum of the given rolls from the target sum gives us the sum of the missing rolls, 24, 12 equals 12. Now, we need to split this sum of 12 across two rolls, and one possible solution is 6, 6. Both values are valid dice rolls since they fall within the range of 1 to 6. Building on the concept, let's examine another example. Here, rolls is 1, 5, 6, the mean is 3, and n is 4. The sum of the given rolls is 1 plus 5 plus 6 equals 12, and the total number of rolls is m plus n equals 3 plus 4 equals 7. The target sum for all rolls is calculated as mean asterisk m plus n is equal to 3 times 7 equals 21. Subtracting the sum of the given rolls from the target sum gives us the missing sum, 21, 12 equals 9. This sum needs to be divided among the 4 missing rolls, and one possible distribution is 2, 3, 2, 2. Each value is within the valid range of 1 to 6, so this is a valid solution. Now, let's consider a case where it's not possible to find a solution. Suppose rolls is 1, 2, 3, 4, the mean is 6, and n is 4. The sum of the given rolls is 1 plus 2 plus 3 plus 4 equals 10. The total number of rolls is m plus n equals 4 plus 4 equals 8, and the target sum for all rolls is mean asterisk m plus n is equal to 6 times 8 equals 48. This means the missing rolls must sum up to 48, 10 equals 38. However, it's impossible to split 38 into 4 values where each value is between 1 and 6, so the output in this case is an empty array. This highlights the importance of verifying whether the target sum can be distributed within the valid range for dice rolls. Finally, let's review the constraints and edge cases for this problem. The input guarantees that m is the length of the rolls array, and both m and n can be as large as 100,000. Each value in rolls and the mean are guaranteed to be between 1 and 6. When solving, we must handle edge cases. For instance, if n is very large, the missing sum must be evenly distributed among n values without exceeding the valid range of 1 to 6. If the target sum for the missing rolls is negative or exceeds 6 asterisk n, it's impossible to find a solution, so we return an empty array. Additionally, we might encounter cases where all missing rolls must be the same value, such as 6, 6, 6. Ensuring that all these scenarios are addressed is crucial for a correct and efficient solution. To solve the problem of finding the missing observations, we need to construct an array of n integers that, when combined with the given m rolls, results in the specified mean. Each of these integers must also represent a valid dice roll, meaning they must fall within the range of 1 to 6. One possible approach to this problem is the brute force method. The intuition here is to generate all possible arrays of size n and filter out those that meet the mean condition while ensuring all elements are within the valid range. First, we calculate the total sum required for all dice rolls, using the formula mean asterisk m plus n. Then, we subtract the sum of the given rolls to determine the sum that the missing dice rolls must achieve, referred to as missing underscore sum. From there, we enumerate all possible combinations of n integers within the range of 1 to 6, checking if their sum equals missing underscore sum. However, the brute force approach quickly becomes infeasible for larger values of n because the number of combinations grows exponentially. This results in a time complexity of 6 to the power of n, making it inefficient and impractical for solving the problem in most scenarios. Instead of brute force, we can use an optimized greedy approach to solve this problem more efficiently. The key insight here is to directly compute the required values by leveraging the properties of averages, thereby avoiding exhaustive enumeration. We start by calculating missing underscore sum, just as we did in the brute force approach. Next, we check whether it is possible to split missing underscore sum into n integers that fall within the range of 1, 6. For this to be valid, missing underscore sum must lie within the range n, 6 asterisk n, which represents the minimum and maximum possible sums achievable with n dice rolls. If this condition is satisfied, we distribute missing underscore sum as evenly as possible across the n integers. This involves assigning each roll the average value, calculated as missing underscore sum // n, and then distributing any remainder, given by missing underscore sum %n, incrementally. Throughout this process, we ensure that all values remain within the valid range of 1 to 6. This approach achieves a time complexity of n, since it requires only a single pass to construct the result. However, it is important to handle edge cases carefully, such as when missing underscore sum falls outside the valid range. Another alternative is the binary search approach, which involves iteratively narrowing down the possible values for each roll. While this method works, it is slightly slower, with a complexity of n log 6, and is more complex to implement, offering no significant advantage over the greedy approach. For this problem, we chose the optimized greedy approach as our solution strategy because it strikes the best balance between simplicity, efficiency, and clarity. The central observation is that the problem boils down to distributing missing underscore sum into n integers within the range of 1 to 6. By leveraging integer division and remainders, we can achieve this directly without resorting to combinatorial enumeration or iterative searches. This not only simplifies the implementation but also ensures that the solution is computationally efficient. The key insights that make this approach effective include understanding that missing underscore sum must fall between n and 6 asterisk n for a solution to exist. If it doesn't, the problem has no valid solution. Additionally, distributing missing underscore sum as evenly as possible minimizes the likelihood of encountering edge cases and ensures that the values remain within the valid range. These observations reveal that the problem is inherently linear, making the greedy method the most natural and efficient choice. When comparing the different approaches, each has its trade-offs. The brute force method is conceptually straightforward but computationally prohibitive, especially for larger values of n, due to its exponential time complexity. The greedy approach, on the other hand, is highly efficient with a linear time complexity of n. It is also relatively easy to implement and directly addresses the problem constraints without unnecessary overhead. While the binary search approach may seem more robust for handling theoretical edge cases, it is harder to implement and slower in practice, offering no real advantage over the greedy method. By choosing the greedy approach, we achieve an optimal balance between speed and clarity, ensuring that the solution is both correct and efficient for all valid inputs. This makes it the ideal strategy for tackling the problem of finding the missing observations. To solve this problem, we need to determine an array of n integers representing the missing dice rolls, such that the mean of all dice rolls, including both the given rolls array and the missing rolls, is equal to the provided mean. Additionally, each individual dice roll must be a valid integer between 1 and 6. The first step in the algorithm is to calculate the total sum of all dice rolls. Since the mean is defined as the total sum divided by the number of elements, we can compute the total sum by multiplying the mean by the total number of rolls, which is the sum of the lengths of the given rolls array, m, and the missing rolls, n. Once we know the total sum, we subtract the sum of the given rolls array to determine the sum required from the missing rolls. This gives us a clear target value to work with as we construct the missing rolls array. Next, we need to verify whether it's even possible to achieve the required missing underscore sum with the given constraints. Since each dice roll must be between 1 and 6, the minimum possible sum for n rolls is n*1, and the maximum possible sum is n*6. If the missing underscore sum falls outside this range, it is impossible to construct a valid solution, and we should immediately return an empty array. If the missing underscore sum is within the valid range, we move on to distributing this sum across the n missing roles. To begin, we initialize an array of size n filled with ones, as this is the minimum valid value for each role. Then, we calculate the remaining sum needed to reach the missing underscore sum after accounting for the initial ones. This remaining sum will be distributed incrementally across the roles, ensuring we never exceed the maximum valid value of 6 for any role. To distribute the remaining sum, we iterate through the array of missing roles. For each role, we calculate the maximum possible increment that can be added without exceeding the value of 6. This increment is the smaller of the remaining sum or the maximum allowable increment, which is 5, since the role is initialized to 1 and must not exceed 6. After adding the increment to the current role, we update the remaining sum by subtracting the increment. If the remaining sum becomes 0, we terminate the loop early, as we've successfully distributed all of it. At the end of this process, the array of missing roles will satisfy all the problem constraints, its sum will equal the missing underscore sum, and every value in the array will be within the valid range of 1 to 6. The algorithm utilizes a fixed-size array to store the missing roles. This array is initialized with ones to ensure that it is valid from the start, as all values are within the allowable range. The algorithm updates the array in place during the distribution step, keeping memory usage minimal. In terms of complexity, the time complexity is O(n), as we iterate through the missing underscore roles array exactly once to distribute the remaining sum. The space complexity is also O(n), as the only additional data structure used is the array of missing roles itself. Overall, this makes the algorithm efficient for the problem at hand. To summarize the approach, the key steps include calculating the missing underscore sum, checking its feasibility, initializing the array, and incrementally distributing the remaining sum. This ensures that the solution is both correct and efficient. Let's look at an example to see the algorithm in action. Suppose we are given roles equals 3, 2, 4, 3, mean equals 4, and n equals 2. First, we calculate the total sum of all roles, 4 for plus 2 equals 24. Next, we find the sum of the given roles, 3 plus 2 plus 4 plus 3 equals 12. The missing underscore sum required from the missing roles is therefore 24, 12 equals 12. We initialize the missing underscore roles array with 1, 1, representing the minimum valid values for the two missing roles, and calculate the remaining sum to distribute, 12, 2 equals 10. Now we distribute this remaining sum. For the first role, we add min, 10, 5, equals 5, resulting in 6, 1, and reducing the remaining sum to 5. For the second role, we add min, 5, 5, equals 5, resulting in 6, 6, and reducing the remaining sum to 0. With the remaining sum now at 0, the algorithm terminates, and we return the missing underscore roles array, 6, 6. This array satisfies all constraints. The sum of the roles is 12, matching the missing underscore sum, and each role is within the valid range of 1 to 6. This example demonstrates how the algorithm efficiently constructs a valid solution by systematically distributing the missing underscore sum across the roles. By leveraging the feasibility check and the greedy distribution approach, we ensure that the solution is both accurate and optimal for the given inputs. This implementation solves the problem by calculating the total sum required for all dice rolls, based on the given mean and the number of roles, including both the provided roles and the missing roles. The difference between the calculated total sum and the sum of the given roles determines the sum needed for the missing roles. First, the code calculates the missing underscore sum by subtracting the sum of the given roles from the total sum needed. If this missing underscore sum is invalid, i.e., less than the minimum possible sum of n roles or greater than the maximum possible sum of n roles, the function immediately returns an empty list, as it's impossible to find a valid solution. If the missing underscore sum is valid, the function distributes it among the n missing roles. It calculates a base value, the integer division of missing underscore sum by n, and a remainder, the remainder of this division. The base value is assigned to all n roles initially, and the remainder is distributed across the first few roles, one additional unit per role, to ensure the total sum matches the missing underscore sum. Finally, the function returns the constructed result array. This approach ensures that all roles are within the valid range, 1, 6, and the total sum matches the requirement. Here, we start by importing the necessary packages and defining the solution class with the missing roles method. The goal of this method is to calculate the missing dice rolls required to achieve a specific mean across all roles. First, we calculate the total number of roles, which includes both the given roles and the missing ones. Using this, we compute the total sum needed to achieve the desired mean. Next, we calculate the sum of the given roles by iterating through the roles array. The difference between the total sum needed and the sum of the given roles gives us the missing sum, or the sum that needs to be distributed among the missing roles. However, before distributing this sum, we check if it's even possible to divide it among the missing roles, given the constraints that each role must be between 1 and 6. If the missing sum is outside this valid range, we return an empty array since it would be impossible to achieve the desired distribution. Assuming the sum is valid, we proceed to calculate the base value for each missing role by dividing the missing sum by n, and we also calculate the remainder, which will be distributed later. Finally, we initialize an array for the result and fill it with the base value. To handle the remainder, we distribute it across the first few elements of the result array. This is done by incrementing the value of the first remainder elements in the array by 1. Since the remainder is guaranteed to be smaller than n, this ensures the distribution is valid and all values remain within the bounds of 1 to 6. Once the remainder is distributed, we return the result array, which contains the missing roles that, when combined with the given roles, achieve the desired mean. This approach ensures that we meet the problem's constraints while maintaining an efficient solution. In the first example, we are tasked with finding two missing roles such that the overall mean remains 4. The input roles are 3, 2, 4, 3, and since there are 4 given roles with 2 missing, the total number of roles becomes 6. To maintain a mean of 4, the total sum of all roles must be 24, as calculated by multiplying the mean by the total number of roles. Next, we find the sum of the roles that are already given. Adding them up, we get 12. This means the sum of the two missing roles must be 12, which we determine by subtracting the given sum from the total sum needed. Now, we validate whether the missing sum of 12 can be distributed across 2 roles. The smallest possible sum for 2 roles is 2, and the largest is 12, so the missing sum of 12 is valid. To distribute this sum, we calculate the base value for each role as 12 divided by 2, which gives 6. There's no remainder since 12 is evenly divisible by 2, so both roles simply take the base value, resulting in 6, 6. Since no further adjustments are needed, the missing roles are 6, 6. In the second example, we are given roles 1, 5, 6, a mean of 3, and 4 missing roles. The total number of roles is 7, and to maintain a mean of 3, the total sum of all roles must be 21. The sum of the given roles is 12. Subtracting this from the total sum needed, we find that the missing sum is 9. This is the sum that must be distributed across the 4 missing roles. Here, we check the range for the missing sum. The smallest possible sum for 4 roles is 4, and the largest is 24. Since the missing sum of 9 falls within this range, we proceed to distribute it. Dividing the sum of 9 by 4, we find the base value for each role is 2, with a remainder of 1. Starting with 2, 2, 2, 2, we distribute the remainder by adding 1 to the first role, resulting in 3, 2, 2, 2. This ensures the total matches the missing sum, so the missing roles are 3, 2, 2, 2. In the third example, the input roles are 1, 2, 3, 4, the mean is 6, and there are 4 missing roles. The total number of roles becomes 8, and to achieve a mean of 6, the total sum of all roles must be 48. The sum of the given roles is 10. By subtracting this from the total sum needed, we find the missing sum is 38. Now, we verify if the missing sum of 38 is feasible. The smallest possible sum for 4 roles is 4, and the largest is 24. Since 38 exceeds this range, it is not possible to distribute the missing sum across 4 roles while maintaining the constraints. Therefore, the output for this case is an empty list, indicating that it's not possible to find valid missing roles. Here, we analyze the time complexity of our solution step by step. First, calculating the sum of the given roles involves iterating through the array, which takes O, M, time if the size of the array is m. Next, validating the missing underscore sum through constant time checks like comparing it against n 6 asterisk n adds only 1 to the overall complexity. The final step is distributing the missing underscore sum into the result array. This involves initializing n elements to a base value, which requires n, and updating the first remainder elements, which also takes n, since remainder is at most n. When we combine these steps, the dominant terms, m, for summing the roles and n, for constructing the result, give us an overall time complexity of m plus n. Now, let's evaluate the space complexity. The input arrays and variables, such as roles, mean, and n, are part of the input and do not contribute to additional memory usage. The solution creates a new array, result, of size n to store the missing roles, which requires n space. Additionally, temporary variables like total underscore roles, total underscore sum underscore needed, and missing underscore sum are scalar and require constant space, or 1. Therefore, the overall space complexity is dominated by the result array, making it n. Let's compare this optimized solution with a brute force approach. A naive method would generate all possible combinations of n roles, each ranging from 1 to 6, and check which combinations sum up to missing underscore sum. This would result in a time complexity of 6 to the power of n, as there are 6 to the power of n possible combinations, and the space complexity would also grow significantly due to the need to store these combinations. In contrast, the optimized solution directly calculates the base value and efficiently distributes the remainder, avoiding the need to generate combinations. This reduces the time complexity to m plus n, and the space complexity to n, making it far more efficient. Finally, let's examine the best, average, and worst-case scenarios for our solution. In the best case, when the missing underscore sum is evenly divisible by n, the required steps still involve m, for summing the roles and n, for constructing the result, as these operations do not change. On average, the time complexity remains m plus n, as it is independent of the specific values in roles or n. Even in the worst case, where missing underscore sum is at its boundary values, the validation checks and distribution logic do not introduce additional iterations or recursive calls, keeping the time complexity at m plus n. Mathematically, summing the roles contributes m, while creating and modifying the result array takes n. Since there are no nested loops or higher order terms, the total time complexity is m plus n, and the space complexity remains n. When approaching this problem, there are several common mistakes to watch out for. First, misinterpreting the mean formula can lead to errors. Remember, the mean is calculated as the sum of all values divided by their count. From this, the total sum of the missing roles can be derived using the formula, missing underscore sum equals mean multiplied by the total number of roles, minus the sum of the given roles. Misunderstanding or incorrectly applying this formula often leads to incorrect solutions. Another frequent issue is ignoring the valid range of dice rolls. Each roll must fall between 1 and 6, and if the missing underscore sum cannot be distributed among the n rolls while staying within this range, the solution simply isn't feasible. Skipping this validation step can result in invalid outputs. Additionally, neglecting to account for edge cases is a common pitfall. Examples include scenarios where n is extremely large or small, the mean is at its boundary of 1 or 6, or the roles array is empty. Testing these edge cases ensures your solution is robust. Mistakes can also occur during the distribution of missing underscore sum, especially when values are assigned carelessly without ensuring the constraints on both the range and the total sum are met. Finally, inefficient computation is a trap to avoid. Solutions that include unnecessary operations, such as sorting, can increase complexity beyond the expected n. It's important to identify and optimize such inefficiencies to meet the problem's requirements effectively. To perform well in interviews with this problem, it's crucial to focus on a few key areas. First, you need to understand the problem constraints thoroughly, such as ensuring that each dice roll falls within the valid range of 1 to 6. Interviewers often assess how well you convert these constraints into code. Additionally, you should be able to clearly explain how your solution handles edge cases. For example, what happens if the missing underscore sum is less than n, or greater than 6 times n? Demonstrating that you've considered these scenarios shows that your solution is reliable. Efficiency is another critical point. Highlight that your approach works in O(n) time by directly computing the missing roles without redundant operations. This demonstrates that you're mindful of performance expectations. Walking through examples is also highly beneficial. By using sample inputs to explain your process step by step, you can showcase your thought process and command over the problem. Moreover, exploring related problems can deepen your understanding. For instance, problem 1221 involves splitting a string based on balance, while problem 1413 focuses on maintaining constraints to ensure a valid result. Problems like combination sum3 or random pick with weight also deal with distributing values under specific conditions. Familiarity with these related challenges can help you identify patterns and refine your approach for this problem. There are alternative approaches to solving this problem, each with its own trade-offs. One approach is brute force, where you try all possible combinations of n roles that sum to the missing underscore sum. While this method is conceptually straightforward, it's computationally expensive, with a time complexity of 6 to the power of n, making it impractical for large values of n. A more efficient method is greedy distribution. Here, you start by assigning the minimum value of 1 to all n roles, and then incrementally distribute the remaining sum to meet the constraints. This approach runs in O(n) time but requires careful checks to ensure that the values remain within the valid range and that the total sum is correct. Another option is binary search, which could be useful if the problem constraints were modified, such as determining the maximum possible mean. However, for the current problem setup, binary search is unnecessary. The key insight to solving this problem is that it boils down to distributing a fixed sum, the missing underscore sum, across n values while ensuring two critical conditions: each value must be between 1 and 6, and their sum must exactly equal the missing underscore sum. Success depends on efficient computation and meticulous handling of edge cases to ensure the solution is both correct and optimal. Great job! We've successfully broken down and solved the problem find missing observations. Remember to focus on constraints, optimize your approach, and practice similar problems to reinforce your understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!